Hi, everybody. I'm Bryce Cottam. I'm a senior architect here at Spectrum Labs.
And I'm John Purnell, and I'm the VP of Data Science at Spectrum.
So we had a few experiences, like Katie said, about cross-team collaboration, and each of us have worked in scenarios where we're on different teams and different companies that maybe didn't have as smooth collaboration, and we thought it was worth sharing some of the things that seem to be working for us. Hopefully, they'll be beneficial for you. As far as an agenda, we'll go over these topics basically using the same vocabulary. You'll notice a lot of the things in this presentation have to do with good communication between teams. Identifying your deployment strategy, like where your model is going to run and how it can be invoked in production. Using the tools you're familiar with, like the things you use every day, or learning the tools you need to know. Culture, which of course maybe should be at the top, because I mean none of the other stuff works without it. And then we'll go into the specifics of a case study that John and I specifically collaborated on and worked out pretty well. So John, you may have a better definition for any of the terms that are on here, but the idea that I had in this slide was that there are certain terms that data scientists use rather casually because they're smart and they understand the math behind a lot of things. But if they translate the idea that is a common term in their vernacular into some engineering term, there's going to be something lost in translation. So we've tried really hard to use the accurate terms for an idea in data science. And luckily, I don't need to know a ton of them. I only need to know about what's on the screen, but they're really handy to know. So like precision and recall and how they combine to make an F1 score. Those are, man, we talk about those a lot, and being able to understand what they are and not have to like look them up, that's important for me. Specifically word embeddings, I deal with all the time. In fact, I was just doing some profiling on our word embeddings. So knowing the difference between glove and BERT and word to vec and stuff like that. John could probably talk more about Bayesian models and evaluation sets, but I'm really glad that he shared with me the specifics of an evaluation set, because in our data curation, when we're getting training data, it's very, very important that if we get duplicate messages that overlap with an evaluation set, that we prune those when we do training. So when we're managing the data that John and his team are going to train on, I need to make sure it's not polluted in such a way that's going to ruin our accuracy checks. On engineering for us, that's about what it covers for me. John, you want to go over the engineering stuff that helps you?
Yeah, I will add on that that I think one thing it's important for not only for the data science team to know, but also like for both the engineering and data science team is the effects, especially when you're working with models, is the effect of sampling. So how it was sampled, when it was sampled. Is it a uniform random sample, or is there some bias that's under there? And especially with evaluation sets, it's important to know that, and to know, on the engineering side, you have those sort of like sniff tests, and that there's a similar thing on the data science side with evaluation sets. When you get metrics back, you need to make sure that they pass the sniff test, and that you're not starting to take actions on erroneous data, or at least on biased data. But, so yeah, so it's a little bit of sharing vocabulary, and then also looking on the engineering side, it's a little bit of vocabulary, and I think behind this vocabulary is the sort of like the patterns and the mindsets that you kind of have going through the work. So just like dealing with sampling and bias and evaluation sets. So I think on the engineering side, the practices of um, like sustainable patterns is something. So there's some things that maybe some folks are familiar with, like GRASP, which is how like object-oriented programming is applied. The solid patterns, which are generally about like having each part of your code do one thing and do that thing right, not overloading it, trying to make things extendable, trying to avoid hard coding, hard coding schemas, hard coding parameters, so it's there's there's a lot of patterns that we've picked up on the data science side from the expertise and the experience of the engineering that's allowed us to, on our training side, even though our training side of the code doesn't directly impact production, we're using it to train the models. We can use these patterns so that as we need to develop new models, or we want to start experimenting with stuff that we see in literature, our code base is already set up to make that easier, so that we don't have to kind of start from scratch or do a huge refactoring on our code in order to accept new things. And we'll talk a little bit about in our use case a little bit about one particular way that we applied that. I think also, and there's I think for each data science team, it's a little bit they have their own constraints, and I think our situation, as we'll go through it and you'll see, has its own unique challenges that may not apply to all data science teams, but I think all data science teams have some sort of constraint. So it is important that there is communication between the engineering and the data science about how big of a model you can have, like how much memory, how much compute resources you can use for that. For deliverable constraints, it'd be about latency. How long can it take to provide a prediction or provide a response? And then the last two things there, I think, are other things like the idea of technical debt, of kind of it kind of leads into like the solid practice of not being conscientious of when you're sort of kicking the can down the road. Sometimes timelines require you to do things a little bit quicker and not necessarily in the most forward thinking way, a long-term thinking way. But you need to be in a practice of keeping track of where that is, so that when you do have the bandwidth down the road, that you can come back to that. So one way of doing that is just having good to-do comments in your code base that you can then reference back to. And semantic versioning is also good for, we find that very important, taking the practices from engineering of semantic versioning, and we apply that to not only just the models that we're producing, but also the training sets that we iterate over, and the definitions that we use for the tasks that we're tackling. So since we're working mostly in NLP space, we're gathering a lot of text data that falls into certain behaviors that we want to classify, and so we have a definition of what those behaviors are. But that might evolve over time. It might change for various client use cases. So having that semantic versioning helps us to kind of track and keep together, okay, this model and this data and this definition go together. And so if we're coming up into a new problem, we know what version of these things to pull together to build a new product, or to build the next version of a certain product. So it's very helpful to bring that in.
Yeah, and let me throw in the additional following simple things like semantic versioning and some conventions on where resources go have enabled us to avoid copious amounts of configuration to tell the production code where to find what it needs for a given model. Following patterns like semantic versioning and directory layout, resource layout, has allowed us to automate the detection of that kind of stuff. Really handy.
Yeah.
So identifying the deployment strategy. John, I think you're the one that brought up, can't you just deploy a Docker image like that gets thrown out a bunch?
Right. Yeah. Yeah. And I think that there's again, there's a lot of situations where that's valid to do. But uh, so to kind of sneak behind the curtains a little bit, you know, a lot of stuff in data science is done in Python. So it's very easy to write some code to pull in some useful libraries, whether it's, you know, TensorFlow and PyTorch, and mixing it with, you know, sklearn, or in NLP you might use spaCy to do some pre-processing and stuff like that. And you can because it's all in Python, and a lot of it's been sort of co-developed alongside each other. You could just easily write a lot of this stuff in Python to get to the results that you want, or get to the model you want. But yeah, then the question becomes, okay, now I need to put this into production, right? So now this needs to be servicing real-time needs. And so why can't we just put it into a Docker image? Is it, you know, so there's a couple of things, right? Which is, one is within, you know, within Python, we're handling how the input is coming in, but that's not necessarily something we can control very easily in production. And so, or the controls for that in production are not in Python, right? And it's not for certain constraints, for certain latency constraints, Python's not the way to go, and just deploying a Docker image is not going to satisfy those constraints. So there's when you start going into the larger context of production, it's not a trivial thing to just deploy an image.
And even if it is deployed in an image, I mean, that only resolves things like, you know, your Python and pip versions and stuff like that, so that they don't conflict with whatever the production environment is, which may have some legacy component that requires an older version of a library or something. But also, you still need to understand how some production system code passes the proper input to the model. Is this over a socket? Do you invoke a Docker container with command line args? Is there a common data store that you're writing to and reading from? All that stuff can, well, they're conversations to have way before you go to production. One of the constraints that I've seen in working with different data science teams is oftentimes data science has like almost godlike privileges to get data, because it's very valuable to get the insights that you can derive from things that have signal in them. And in production systems, lots of times for security, data that has signal in it isn't available because, you know, man-in-the-middle attacks or SQL injection or whatever it is. If the sensitive data is kind of partitioned off, then you don't have to worry about it leaking in production. But now imagine a scenario where a data scientist creates a model that's able to detect fraud really well, but it has to have like the social security number of the user or something like that. It's not much signal in a social security number, but something that's private, that can be a problem. So talking about that upfront can help you kind of box in the approach you take to creating a model, or may have your production system, you know, reshape so that it can accommodate the needs of the model. Either way, you just need to know about it. Mm-hmm. A big deal is pre-processing. We'll go over this in a bit more detail in another slide, but it is really common that data scientists spend a good amount of time preparing the data that they're going to train on or evaluate. And there may be specific encodings, like one-hot encoding as an input, rather than, you know, consuming some more raw input and doing that transition to one-hot encoding inside the graph. So when there's a misalignment in that pre-processing, you'll see maybe great results in the data science, building side and saying like, okay, this model's all ready, but that performance is way lower in production. And oftentimes, when I've been pulled in consulting scenarios, it's been a significant misalignment in the pre-processing.
Mm-hmm.
So, yeah. So the sort of life cycle of the data flow for us.
Yeah, and this is so again, since we're working mostly in NLP, this is sort of a high level of the steps in a possible like NLP process, and I think some things like to call out, right, like so we use models that use word embeddings like glove and BERT and stuff like that. So you have language models, and so the more languages you want to support, the more difficult this can become in terms of resources to manage, and that's just something that it may not be trivial to do in again like in a single language or a single framework. And so you can kind of see there's 2 points of dotted lines, which is generally for us, this is generally sort of where we sort of create these contact points between production and data science. And so on the data science side, we're using our environment and our packages to develop models and develop rule systems and context aggregation. But then those have to accept some input from production. So like on the production side, we may not be able to make assumptions about what language is coming through, or certain artifacts inside the language that we need to pre-process, metadata that needs to be cleaned up. And so really we need a production level system to handle that and be able to switch between the languages or switch out resources that are needed for that. And that feeds into what embeddings get loaded, and that determines what goes into the models. So keeping that separate from the models makes both our lives easier, and it also allows us to optimize where we need to optimize. But it does have the overhead of that there needs to be good communication coordination about, especially on those data points, about what data is coming across and what format and stuff. And the use case we kind of go a little bit through, or later on we kind of talk about how we tackle this in a way. But there's because these different parts of the process have different sort of goals that they want to optimize for and different constraints. It doesn't always make sense to put all of it on the engineering side or all of it on the DS side.
So specifically embeddings, yeah, we've had some fun managing multiple embeddings, like one per language, and fitting that in memory. And so being able to separate out somehow in the model, like some scenarios, this may not be ideal in every scenario, but having a different model for a different language. So a Russian model that aligns with a Russian embedding, and then a Spanish model that aligns to a Spanish embedding, both detecting the same behaviors, can be really helpful in segregating the resource demand of the model. So we can sort of like partition or load balance and direct traffic based on language. And then all the Russian stuff's over here, all the Korean stuff's over there. It's not a one size fit all, but it really helps to be able to separate that sometimes.
Hey guys, real quick on that slide, we're getting a question. Can you please elaborate on context aggregation?
Yeah, so for context aggregation, so that's what I mean by that is, so our models and your models might work on, say, a specific piece of text or like a single isolated piece of text, but you might have a certain context that you want to then aggregate that that signal over. So let's say you're looking at a forum thread. So you have multiple posts. So you might have a model that can work on a single post, but then you want to perform some analysis on the whole thread, right? So maybe something about like the toxicity of the thread. Maybe you want to kind of look at how it's increasing or decreasing or fluctuating over time. So that the context in that sense would be the thread, and you're aggregating across all the posts to get a thread level analysis. So that's like an example of what a context aggregation would be.
Bayesian models to the rescue.
Yes, yeah.
Awesome. Do we have other questions on this one, Katie?
Yep, that's perfect. Thank you.
Cool. Okay, so people are most efficient when they're using things that they're familiar with. You know, the latency that comes with the learning curve. And essentially, there are two ways to always use the thing you're familiar with. You either get familiar with the thing you need to use, or you use the thing you're already familiar with. And each scenario would dictate a different approach. But in our case, we've found it best, thus far anyway, to have the data science team use what they're familiar with. We've talked about it several times, Python and related tools, pandas, stuff like that. And in our production code, some of those don't scale as well. And so we wind up using different languages like Scala and Go and things like that. But one of the things that's really handy in a scenario where you're just using the stuff you're already familiar with, which almost inherently means people are using different tool sets to accomplish maybe the same goal, like detecting hate speech. It's really handy to have checks that are essentially like unit tests for the different language implementations of the logic. So for instance, having a config that says, okay, if I give this input to the code in Python, I expect this output. And it turns out you're going to expect the same output in Go and Scala and, you know, .NET or whatever else you're using. This makes it really easy to automate checks. So when features get enhanced, one of the obvious scenarios where this comes in handy is pre-processing the text. So we'll do cleaning on the input before we pass it to a classifier. And this includes things like stripping out HTML tags and flattening lines. So you're taking out new lines in it and removing certain punctuation. Some punctuation is pretty handy to have in there, but yeah. If you're doing like, is it word stemming? Did I use the term right, John?
Yeah, stemming or localization, yeah.
So any of that kind of thing, this makes it easy to detect, oh, well, our production code's not up to date with the pre-processing that the model was built off of. So we need to iterate on it until we can pass these tests.
Mm-hmm. Yeah, it's it's important to do. Yeah, you can kind of get surprised by how different languages handle what look to be the same exact process.
Like regexes that actually are formatted different.
And so yeah, so it's really important to make sure that you have these kind of checks and to have that consistency across your languages.
We've got a question on that one. Sorry. How do you convert Python ML packages to Go?
Good question.
Yeah, so there are, the approach that we have taken is, so we use TensorFlow in pretty much all our classifiers. And there are libraries generally for the different languages that you're going to be executing that classifier in. So we're not really doing a translation of Python code or a package in Python into some other language. And Josh, our CTO, is the one to talk to you about the Go code, because I try to make sure I don't have to touch that. But the support that's already in that language from the community, or thin wrappers that we implement to enhance that functionality, is generally what we rely on. So if there's no support for the backing data science technology that we're using, like TensorFlow, in a given language, it would probably disqualify that language from the engineering side and say, like, well, it'd be great if we could use, I don't know, Rust, but there's no TensorFlow library. So it turns out there is, but you know, in that scenario, a brand new language that doesn't have the support. So we're not doing any kind of cross compilation or translation.
Right, exactly. And that I would say, so when you know, and this kind of goes for, you know, whether you're using TensorFlow or honestly, if you're using TensorFlow or sklearn or PyTorch or, you know, Cafe or whatever you're using, whatever framework you're using to generate your models, there's two ways you can generally go about, which is either when you're trying to do it, trying to load it for inference in another language, you're either using the native interface in that language if it exists, or the alternative is to use something like Onyx format. But that even that format, right? So that the Onyx format gives you a little bit more flexibility, but you still need within that language to have some way of running that and executing that with the constraints that you might have. So this is again, it's another thing that that the engineering team needs to be aware of and look into to make sure, because we thought it was one thing that we thought originally. We thought, okay, you know, we've got Onyx, it's a great thing. Microsoft supports it to have this flexible model format, but it's not necessarily fully supported in lots of different languages, especially if you want, you know, high performance, or you want GPU support with the latest tools. And then, you know, you also get into a versioning thing, which is what versions of your original frameworks like TensorFlow and PyTorch are supported with the current version of Onyx or the current native interface from other languages. So there's a lot of, there's a couple things to keep in mind there. It's not insurmountable, but there's enough gotchas that it does require, you know, everyone to be to do their due diligence.
Other ones, Kate?
Yeah, I think that's it.
Okay, so culture. As I mentioned on this front, it's maybe the most important, and that's essentially having the willingness to learn from other people and not, you know, assuming that you know everything that you need to know. Those seem like they would be basic table stakes for being, you know, in any scenario where you collaborate with others, but turns out people don't do that all the time. So I'm really, really thankful that our data science team is so nurturing and you know, willing to explain and boil down these concepts that they deal with to us. We've got a number of PhDs, and so that can be kind of a imbalance in ego in some places. I've worked at them where there's just this insulting, like, nah, I solved this model and, you know, it's your job to deploy it. And that sort of best intent, like, you know, sharing values and purpose generally helps the collaboration go better. If there's some kind of tension between the teams, like, you know, you're competing for a priority, that can be a problem. So a scenario that I remember in a couple of companies ago that surprised me was tension between the infrastructure team and the engineering team. And I thought it just was asinine that there was, like, you know, they would get in fights about, you know, where something was deployed or how something was deployed. You know, just egos. So taming those down can really, really be beneficial. It's so subtle and it's such a people thing, and not like a use this technology or that tool, but really, really important. And in terms of the teaching each other, there may be things that, like the data science or engineering teams may benefit from uh, in just viewing a day in the life of the other team. So one of the main approaches that we've used to cross-pollinate ideas is brown bags and data science jams. So in a brown bag, we're just going over like, hey, this is how you run Spark, on your local machine, and this is how I took this input and transformed it and blah 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 with very little effort. Um, that can be really handy for a data science team to know, or data science team going over, all right, well, this is what I did to transform the input into something that I can detect the signal in, and just watching the steps that they go through can really be enlightening for our engineering team to be like, oh, okay, all right, you had to kind of bend over backwards to get this, and maybe you know an easier way, or you're like, we should be doing what they're doing in the production code, because consistency.
Exactly. Yeah. Yeah. I can't overstate the value of the brown bag data science jams, because it's not only good for knowledge sharing, but it's also like an open forum for everyone to throw out questions, and to to have sort of tangents and conversations about like, oh, like how would this apply to such and such, right? And I think and one concrete pain point on the data science side is I think when you're learning data science, there's a lot of basic data sets. Like there's the iris data set and the MNIST data set, right, which are like super trivial. They could fit in the memory of your phone, right? But in reality, when you're dealing with certain projects, especially around text, it has just a huge memory footprint, right? And like we have data sets that are usually hundreds of megs. It's no longer trivial when you're trying to process that or go through that or do some transformation across the whole data set. And so even sometimes we've just had sessions where where we've shared our approaches just to handling large files, and like command line tools that we use and stuff that's in Python that we can use, and just how we can mix that to work better at scale. So it's those kind of meetings are really great, and then to that point of not just throwing things over the fence, right? So collaborating together gives an iron sharpens iron kind of approach, which is that we all like Bryce was saying, we kind of all learn how to do our work better, how to do it a little smarter, and it allows us to also see each other's pain points and realize. So like one thing that's been really great is there's been mutual pain points that we've then gone and built a tool for, so that not only was it a tool that helped to develop production tools, but then it turns out that we were able to also use that for our data science side to do some various experiments. So it not only fosters innovation, but also just efficacy in our work. Right? I'll throw out the principle of best intentions, which I give our CTO Josh credit for, at least he's the person that I heard it from first, which is especially because we're a startup, and I think and then just because you might have conflicting priorities, there's going to be times when one team or both teams are going to be in a situation that's not desirable, either time-wise or resource-wise. And it could be a very stressful situation that you now have a significant challenge to overcome in a very constraining way. It might be that you have a very tight deadline, much tighter than you usually do, or it might be a completely new application that you need to get off the ground very quickly. A lot of that can happen, and there can be a tendency to blame someone for putting you in this situation. And so the principle of best intentions is that when we're in those situations, we know that we're we're typically in those situations for the good of the company, or for the good of the client. And it's not that anyone in the company is, either doesn't care or is actively antagonistic against us, right? It's more of that they're trying to make the best decisions for the company. And so we should definitely, and I'm not saying you shouldn't push back and there shouldn't be discussions about this, but when we're in these situations, this is part of our grit and collaboration values, which is that, you can't fume and hold grudges, right? It's you realize that, if you have good communication, you realize, okay, we're doing this for the best interest of the company. And so you put your focus on getting the job done, attacking the challenge, delivering the deliverable, and not, and kind of taking a step back, taking the ego out, and not attacking each other and breaking down those relationships, right? So it's it's important. Like, it's important to kind of have that mindset when you go into that you don't immediately start being antagonistic to other people, but also that you be collaborative and it's sort of a benefit of the doubt kind of intention.
I think our stand-ups have been really beneficial as well. So if you have large teams, it's fairly impractical to have everybody in the stand-up, but we have once a week, everybody, at least our two teams, engineering and data science, are together to give updates. And it is quite often the case, or at least often enough, that some new enhancement is coming to a model that triggers, like, I don't think anybody, if they didn't know about it, would have seen it coming, but something that makes me like, oh, okay, so you need this now. Like, there's a different pre-processing that I need to do. Okay, good deal. And, knowing that in a regular cadence, rather than some kind of formal, like, release planning or feature planning or something like that, is really handy for staying in sync. And it also gives opportunities, I think, to ask for, like we said, expected input, or given input and expected output across languages. They're having ad hoc calls and status meetings where you're together gives an opportunity to grab the output. What's the sample set that you used, and what are the results that you got? As I implement, the engineering side, I want to check that I'm getting similar or the same results. So anyway, if you had to, like, call somebody up or send a formal request for something like that, the likelihood of it coming together is lower.
Mm-hmm.
Okay, so our case study, this one's fun. So you'll have to forgive the implicit nature of the shapes. The idea here is that we have 3 models. We actually have tons, but each model is shaped differently. And, maybe they're all trying to detect a behavior, but, the signal for one behavior may include inputs across the board, and another one may be simple inputs. Some of it needs different pre-processing. So their inputs are different shapes as well. And no big surprise, their outputs may be different. So in the bottom, that would be the context analysis. There's, like some kind of prior, well, it's the posterior. In this case, that would be translated to prior in the input. All right, so it's really likely, if you have more than one classifier, that you have something that looks like this. Not everything takes the same input. So the simplest or most direct way to handle this is to have code that knows, like, code A knows how to prep the input and hand the input to model A, and it knows how to read the output. Handler B, production code B, knows all about, classifier B. But one of my favorite quotes about engineers is that good engineers are lazy. They want to solve a problem once and, reuse that. So I would really love a happy handler that happens to know how to talk to any given model within some, some constraints. So we introduce the self-describing model. Now, I think it's true in the graph of pretty much all formats. John, you correct me if I'm wrong, but there are operations in the graph and you can name them. And at least in TensorFlow, there are constraints on what can be in the name of an operation. There are reserved characters and things like that, patterns that you need to avoid so that you don't fool the graph. But we can assign a name that's descriptive enough so that when my happy handler looks at the model, I can detect what it needs as input and what it's going to give me as output. So there are 4 components to this. John and I collaborated pretty significantly on, and also Indrajit, a number of people on our team worked together to identify this, but there are essentially 4 components that we identified that would allow us to evolve our models without production code changes. And that reduces so much of the friction of releasing code. So the first part of a name in an operation is the direction of what it's working on. It's either input or it's output. There are tons of other operations in the graph that maybe don't follow this naming convention, but these are signals to production code that I need to feed something or read something with respect to this model. Then there's scope. So we can pull data from lots of different places. And we have a handful of predefined areas to pull data from, like the message. This might be the content that the text is in, the language maybe of the message. It could be stateful tracking that's not part of the input that we get at runtime, but we can go read, like a prior for a Bayesian model. Some of our classifiers actually ask for the output of other classifiers. So that would be like a score or an attribute, like metadata. Some clients are able to give us metadata that is really, really helpful in making the determination of the behavior, like account created day or number of posts for a given user. Then there's format. Some of these formats are obvious, like embedded text or raw text, but some of them were pretty interesting to settle on. Timestamp and JSON were pretty fun to, by fun I mean a nightmare, to identify the proper input. So from an engineering perspective, I'd love to hand just an ISO formatted timestamp to a model, but the ISO standard one that doesn't have a day of the week is missing information the data science would really need. And also, it's not super optimal to have TensorFlow parse a string. So we wound up splitting up things. For instance, in a timestamp, we have 5 fields. There's the year, the month, the day of the month, the day of the week, the hour of the day. Did I miss one? No, I think that's it. And so these are just in positional indexes in an array. JSON's a little bit more involved, but it works, so it's pretty cool. Then the last one is the key, the specific identifier for the piece of information that the classifier wants. So this might be the metadata user sign-up date or the name of some other classifier to read the output of. So some concrete examples are, I want the input from a message. I want it to be formatted in text, and I want it to be the clean text. Other things, in the bottom are a lot more fuzzy. They're, like the user sign-up date and how it's formatted. We happen to have not too many outputs. There's a confidence in the assertion that a given input matches the behavior we're looking for, and then posterior for stateful tracking of like the toxicity of a thread or the reputation of a user.
The real real benefit there, like you said, is that, different tasks, different, we have, for different clients, right? They'll have nuances to their data, nuances to what data they provide, and having just this standard, having these standard ways of handling different formats and different scopes, makes it much easier because it's a one-time upfront cost, and then whenever we create a new model for a specific use case or client, I know that I can just name my tensors with this format and I'll get the data that I need, and I know the format that it's going to be coming into the model at. So also within my architecture, I can have predefined, subgraph architectures for handling that. So that I can, this goes back to like the solid principles, right? So that on my side, on the data science side, we have easily reusable code, extendable code for handling this. And now that we have this set up, it's the way our code's set up. If we do have a new format, that we want to support, it's much easier to handle. And it's since we're not hard coding it for each client, we don't have to start from scratch each time or have duplicate code everywhere.
Yeah, it reduces a lot of the friction in feature enhancement. So I don't know, this is actually the case study that prompted the idea to share ideas about collaboration across teams.
I won't call out specifically on this, which is, some might think that, you might have just like a separate config file that goes with your model. That introduces, some possible decoupling issues, which is that if you don't make sure, if you're not 100% sure that the config file mirrors what's in your model, then you're going to get errors when you try to load the model or try to use it. So by having this stuff defined inside the model itself, so Bryce, when he loads the model, he can read the tensor names, then for certain that's exactly what the model is expecting and was trained to expect.
Yeah, it helps avoid typos and stuff like that in metadata deployment descriptor. Katie, you were about to jump in?
Yeah, it's awesome. And I got to witness this project in action. And I always say their collaboration makes my heart happy, but it's very true. So we actually have some good questions from our attendees today. So one of them is, how do you do QA and testing, whether it's unit testing or something else? And this is specifically for the ML algorithms.
Mm-hmm. So on the ML algorithm side of things, I think there's a couple ways you could do it, right? So for the implementation of the algorithm, right? So we have various synthetic data sets that we've pulled. We try to also have real world data sets, but usually the synthetic ones can help you get the clearest picture that what you're training your model for is going to capture what you're looking for, right? So like one important thing in our work is properly leveraging metadata. So we have a mechanism. So in addition to the NLP processing with word embeddings and stuff like that, we're also pulling this metadata. So we have these small data sets that we can use when, if we do a code update, we could run the synthetic data through there, make sure we're getting the same results. And so that kind of provides one way of doing sort of unit testing against like the metadata. And then I would say, and then on the other side, or a different angle of like QA testing against the model itself that you've produced, this goes back to evaluation sets. So it's really hard to understate the importance of having multiple, or at least one solid evaluation set, but probably multiple ones. So we have evaluation sets to make sure that we're performing as expected across the distribution of data that the model is exposed to, that it will, given key examples from the particular task for the particular client, for key important data sets that we're doing exactly, we're returning the results that we should be, we're catching what we should be, and we're not falsely triggering on what we shouldn't be. So we have these kind of multiple evaluation sets to make sure as we iterate the model that we make sure we're still hitting the targets that we need to while improving general metrics. And we do have unit tests, like Bryce was talking about earlier. We do also have unit tests that are kind of shared, so that we make sure that, particularly like in pre-processing when we're preparing the text and stuff, we make sure that we get the same results. So we'll have the same tests, like the same input-output text pairs, to make sure that the different systems are doing the same.
So one of the things on the engineering side, I remember the first time when big data was a huge deal and people were really mystified by it, and I did consulting. One of the questions that people would ask me was like, how do you test that? Like, they were under the impression that a unit test would wind up testing that Spark is doing what Spark is supposed to do. And I remember it being hard to for people to grasp that, no, you shouldn't be testing that. You should be testing that your code is feeding Spark the right thing, and interpreting it, its output and things like that. The same thing has applied to a lot of the unit tests that I've written, in that I actually execute a model. Like I read in the graph and I really feed it data and pull what comes out. But what I'm testing in that scenario isn't the accuracy or the precision or recall of the model. What I'm testing is that on a coarse grain level, if I hand something like a really nasty message, that it's going to give me something, I don't know, greater than 75% confidence that that was toxic, or at least that I have the shape of the output in input that I expected. Really executing a model in a unit test, I think, is way more reassuring. Maybe it's just a personal thing that I just want to know that I could mock the model, but if I really feed it in a unit test, then I know it's probably going to work in production.
I think there's a second part to that question, which is, how do you make decisions around investing in machine learning infrastructure, for example, features, bank, prototypes, deployment, framework? So how do we choose our infrastructure and our tools? So it's like an ROI number kind of thing, right? So there's a lot of tools out there that are very useful, but maybe very narrowly defined or very narrowly applicable. So there's and also it depends on sort of the impact on the metrics. So if there was, so to kind of put a little more concretely, like if you have a tool that's very reusable, very widely applicable, that you can use, like sklearn, right? Like can produce some some processes that are very useful, reusable again. Then and it also has like there's good support for that with building into Onyx and stuff like that. It's so then that makes it more likely an easier barrier to bring it into the system. You might have a package though that's only been written in Python that doesn't produce doesn't have results that are in an easily consumable format, or it can't be translated easily to other ones. Like maybe there needs to be an inference engine, and that doesn't exist in other languages. So then your barrier becomes very high to integrate that into your whole system, and so that's going to lower your ROI on it. So those kind of systems would have to have a dramatic impact on our models and our performance. warrant the effort to support that or figure out how to support that. So I think it's sort of a there's also things that like there are certain things that we can use in development and prototyping that we don't need to consult with engineering team about. So when you're talking about hyperparameter tuning, right? Whatever tools we use for that is completely on the training side. That doesn't have anything to do with inference time, or doesn't have any impact on inference time. So so we can use whatever we want with our environment there. So I think there's also a good distinction that we were actually talking about in preparing for this, which is that, Bryce and I are both at sort of an architectural level. So we're having discussions about what tools to use, right? And what code to write for this. And that's part of our role to make those decisions and then provide the set of tools, for our teams to use. So it shouldn't be like, for individual contributors, it hopefully shouldn't be so much of a burden that they have to figure out these kind of things. But then there should also be the forum that if they find that there's some new tool that would give them a great performance and stuff, and a great impact, then they can bring that to us and we can figure out how we can use that or what the level of effort is there. So we talk about the importance of team structure, and that's one thing that's important about it is to, you want to enable your teams as much as possible. But you don't want everyone to try to be, figuring out how to make all these tools work together. So that's like coming up with this naming standard was one way that we work together to provide, a handle for our teams to develop the code and the tools for working together.
One scenario I can think of with that goes back to your ROI and what frameworks or tools or hardware are appropriate for a given scenario. One that comes to mind, John, was a surprising finding that we had when we were just experimenting with scoring at scale. And when you're using, a couple hundred machines to score a huge corpus of data, we didn't want to take forever. And so we had originally provisioned GPU instances because, hey, they're faster. But we found it was not so much faster than CPU in this scenario to be cost effective. And that the CPU actually performed pretty darn well if you had enough nodes. So just experimentation and metrics and measuring is something that from a hardware and infrastructure deployment perspective has driven some of the direction that we go in. GPUs are a lot more useful on training. But there are still scenarios where we use them in inference and their performance is beneficial, but in a number of scenarios, it was about as effective to use a few more machines than CPU.
Yeah, good point.
Awesome. Well, we are just a minute over time. So with that, I want to give a huge thank you to both John and Bryce for talking to us today and letting us in on some of these collaboration tips. And like I said, we did record this, so we'll be sending it out. And thank you so much to all of our attendees for logging in and listening. We're hoping to see you soon.
Yeah. Thank you, everyone.
Thanks, everybody.
Have a good one.